So good morning students, myself this is Sachin Arayana. I'm working as assistant professor in the department of EEE, Institute of Technology and Engineering, Tadepalgudam. So today I'm going to discuss about one topic in electrical circuit analysis 1. So the topic is the maximum power transfer theorem cases. We have different cases under maximum power transfer theorem here. So based on maximum power transfer theorem, here the name itself says power transfer. So if you're taking any electrical circuit, always the power is transferred from source to the load. So if you're taking a mobile charger, so the power is transferred from charger to the mobile battery. Likewise, if you're taking the generator supplies the power, so that is transferred from source to the load. So in case of amplifier also, so the power is transferred from amplifier to the speaker. So this is the power transfer. But here the problem is, the question is arise like under what condition, so the maximum power is transferred. Under what condition, so the maximum power is transferred. That is I am going to discuss with the help of different cases. So here we have different cases here. Every case depends on type of system as well as a type of load as well as a variable parameter here. So if you take in the first case here, the type of network is a DC network and the type of load is a resistive load and the variable parameter is here resistive load. So that is based on type of system, based on type of load and based on variability. So the case depends, as well as based on this we are going to derive the maximum power transfer condition. So coming to the case 2 here, the type of network is AC network and the type of load is a resistive load and the type of variable parameter is here is a resistive only. So coming to the third case, again the type of network is AC network. So the type of load is complex load. So complex load is nothing but is a combination of resistive part as well as inductive part. Under this part, the resistive load is considered as a variable parameter. That is the third case. So the fourth case is again the type of network is AC network and the type of load is complex load and here the variable parameter is inductive load. So coming to the last case, so that is a combination of both the loads, both resistive load and inductive load, both are considered as a variable parameters here. So for all these cases, now we are going to derive the maximum power transfer condition. You know the maximum power, the name says always the power is transferred from source to the load at what particular value of load. At one particular value of load, the power is transferred from source to the load. So that particular value of load we are going to derive. So coming to the case 1 here. So under the maximum power transfer theorem, this is the case 1. So DC network and the type of network is DC network. The type of load is resistive load here. So they already have discussed already in the last class. So again we are going to see here. So this is the DC networks. The DC network has a DC voltage source in series with the equivalent resistance. Here actually this is the Thevenin's equivalent circuit. So Thevenin's equivalent circuit. So Thevenin's equivalent circuit. So before getting the power transfer condition, maximum power transfer theorem or maximum power transfer condition, first we need to get the Thevenin's voltage, Thevenin's equivalent circuit, like it consists of the equivalent voltage and equivalent resistance. So we need to determine with the help of Thevenin's theorem. So this is the Thevenin's equivalent circuit. From this circuit, now we are going to derive the maximum power transfer condition. So this is here the type of network is a DC network. It consists of a DC voltage source in series with the equivalent resistance and the type of load is resistive load. Here the load is varying. Now we are going to derive at what value of load. The maximum power is transferred from source to the load. That is what we are going to derive here. For this we are applying a KVL here. Close to the network is IL. So can write IL is the voltage. So the voltage, that is the equivalent voltage by the total impedance, that is R by R plus RL. So IL equal to V by R plus RL. So this is the current that is flows to the load. So again, the power delivered to the power consumed by the load is power equal to IL square into RL. Instead of IL you can put V by R plus RL whole square. So you can get the power equation is power equal to V by R plus RL, so whole square into R. So this is the power equation. Now we are going to derive the maximum power condition. So for deriving, we are using the differentiation here. So differentiation of power with respect to the variable parameter. The variable parameter is here RL. So differentiation of power with respect to RL and then equated to 0 here. So here the differentiation is used to get the maximum or minimum point. So that's why we are using the differentiation here. Differentiation of power with respect to RL and equated to 0 here. So why are equating to 0 here? Because at the maximum or minimum point, at the maximum point or minimum point, so the slope is 0. The slope is 0, that's why we are differentiating the power with respect to the RL and equated to 0. So after equating to 0, we'll get, this is the condition, so the load resistance is equal to R. So already this topic is already discussed in the last class, so that's why just I'm summarizing this case. So RL is equal to RL here, the load resistance is equal to RL. So when load resistance is equal to RL, when a load resistance is equal to R, so by that time the maximum power is transferred from source to the load. So that is the statement here for DC network. So coming to the case 2. Case 2, now this is going to derive. So here the type of network is AC network. The network has AC voltage source in series with the complex input impedance, source impedance. The source impedance has resistive part as well as inductive part here. And the type of load is resistive load, and the resistive load is varying here. Now here also we are going to derive. So what is the condition? What is the maximum power transfer condition? What is the maximum power condition? So at that condition, the power is transferred from source to the load. So again, just application of KVL here. You can write IL equal to IL bar, because this is the AC network. It has impedance. It has source impedance. Thus I am writing IL in phasor term. So IL bar equal to, so the total voltage is V equivalent or VTH by the total impedance. So R plus, so JX plus RL. So this is the load current. This is the load current just by the application of KVL. From this I am writing IL bar, the magnitude of current. So that equal to, so V by square root of real part square. So R plus RL whole square plus X square. So this is the magnitude of current. From this I am writing power equation. So power. So this is the power consumed by the load. So power or load power. So PL equal to, so modulus of I square into RL. So instead of I, we can put, so PL equal to, instead of I, we can write, so V by, so square root of R square plus, square root of, so R plus RL whole square plus X square whole square I square. So into RL. So from this you can write, so V square by, so R plus RL whole square plus X square. So PL equal to X square into RL. So X square into, so V square by R plus R whole square plus X square into RL. Now, so we need to get, so maximum power transfer condition. For this I am differentiating, so load power with respect to the variable parameter. So the variable parameter is here RL. So DRL equal to 0. So differentiating of power with respect to RL and equated to 0, that gives the maximum power transfer condition. Now, so differentiation of PL, that is, so V square by R plus RL whole square plus X square into RL equal to 0. Now we can use, so differentiation of derivative of U by V rule here, U by V, that is, so V into, so differentiation of U, that is du or V U dash minus U into, so differentiation of V by V square. So by using this formula you can differentiate, so above expression, that is, so directly I am writing here, so R plus, so V is nothing but R plus RL whole square plus X square, this is the V into V. So into U is nothing but V square into RL, where V square is constant. So V square into differentiation of RL with respect to RL, that is 1. So minus, so U into, so that is V square into RL. So differentiation of V, that is differentiation of V means R plus RL whole square. So X is again constant, so differentiation of constant is 0. So we can do differentiation for the first term. We can write, so X square, differentiation of X square is 2X. Likewise you can write 2 into So R plus RL, that is equal to 0. That is equal to 0. From this, so by solving this equation, we will get, so by solving the equation, we will get the load resistance. The load resistance equal to square root of R square plus X square. So this is the maximum power transfer condition for the case 2. So the type of network AC, and the type of load is resistive load, and variable parameter is resistive load. So for this, so when load resistance equal to the magnitude of source impedance, the load resistance equal to the magnitude of source impedance at this condition, so the maximum power is transferred from the source to the load. So this is the second case. Now we are going to discuss third case. So this is the third case. Again here the type of network is AC. AC consists of AC voltage source, and the source impedance is R plus JX. R plus JX, that is the complex source impedance, and the type of load is complex load that consists of resistive part as well as inductive part. Here under these two parts, resistive part and inductive part, now I am taking resistive load as a variable parameter. Again just application of KVL. Again write down the expression for current, that is IL bar. Again the type of network AC, that's why I am writing IL bar, that is phasor. So IL bar equal to, so V equivalent voltage, that is V by the total impedance, that is R plus so JX, R plus JX plus so the load resistance R plus JXL. This is the load current just by the application of KVL. Now from this I am writing the magnitude of current. The magnitude of current IL bar. So the magnitude of current IL bar. So from this you can write, so V by, so square root of real part square plus imaginary part square, that is R plus RL whole square plus X plus XL whole square. So this is the magnitude of current. From this, so form the power equation here. So the power consumed by the load is, always the power is consumed by resistive load here. That's why I am writing load power equal to, so IL square, modulus of IL square into RL. So instead of IL you can write IL square, you can write directly. So V square by so R plus so RL whole square plus X plus XL whole square, so into RL. Now to apply the differentiation with respect to the variable parameters, the variable parameter is RL, so then equated to 0 for getting the maximum transfer condition. So the maximum transfer condition, so for that I am differentiating the power with respect to the variable parameter, that is RL, and equated to 0. So d by, so differentiation of power. So the power expression is V square by, so R plus RL plus R plus RL whole square plus XL plus XL whole square into RL equated to 0. Again apply the, so differentiation of U by V rule. So we'll get, so R plus, so RL whole square plus X plus XL whole square, so V into, so differentiation of U. So where V square is constant, so V square into differentiation of RL with respect to RL, that is 1 minus U into V square into RL, and differentiation of V under V. So here X plus XL whole square, that is constant, so we can differentiate for the first term, that is, so 2 into so R plus RL, 2 into R plus RL, so 2 into R plus RL, and differentiation of RL is 1, RL equated to 0. So equated to 0, then we'll get the expression as already mentioned below, that is, while solving this above expression, we'll get load resistance equal to, so square root of R square plus x plus xl whole square. So this is the maximum power transfer condition for case 3. So the type of network AC network, and the load is complex load. Under complex load, the variable parameter is RL. So when RL equal to, so the magnitude of circuit impedance as seen by the source. So RL equal to square root of R square plus XL whole square. This is the maximum power transfer condition for the case 3. Likewise, we will see the next case. So this is the next case. So again, the type of network is AC network. So the AC network has input voltage, the source input AC voltage, and input impedances are equivalent impedances R plus JX. That is the complex impedance, complex input impedance. And the type of load is complex load. So type of load is complex load. So under complex load, now the variable parameter is inductive reactance. The variable parameter is inductive reactance. Now RL is fixed. When inductive parameter or when XL is varying, so at what value of XL, so the power is transferred from source to the load. That is what we are going to derive. Again, just apply the KVL here. By the application of KVL, that is IL. You can write IL bar equal to supply voltage or equivalent voltage V by, so R plus total impedance, V by total impedance. So R plus JX plus RL plus JXL. So this is the total impedance. So voltage by total impedance, that gives the current. Now after this, you can write the magnitude of current. So magnitude of IL bar you can write, so V by square root of R plus, so real part square, so R plus RL whole square plus X plus XL whole square. This is the modulus of current. From this you can write power expression. What is the power consumed by the load here? Even we are having two parts here, resistive part and inductive part. Only the power is consumed by the resistive part only. So no power is consumed by the inductive part. So the inductive part is used for storing the power, storing the energy, and again it gives back to the source. But it never consumes the power. Only the power consuming element is resistive load here. That's why I am writing the power expression is power equal to load power equal to, so modulus of IL square into RL. So instead of modulus of IL square, you can write here V square. Modulus of IL means V by square root of R plus RL whole square plus X plus XL whole square. So IL square means V square by R plus RL whole square plus X plus XL whole square. Into RL. Now this is the power expression. Now I have to find out the maximum power transfer condition. So I have to apply the differentiation of given power equation with respect to the variable parameter here. The variable parameter is here XL. So we can differentiate the given power, load power, with respect to the variable parameter. Here the variable parameter is inductive reactance. That is XL equal to 0. So differentiation of power with respect to the XL equal to 0. So differentiation of XL, so the power expression is, so V square into, so RL by, so R plus RL whole square plus X plus XL whole square. That should be equated to 0. So where equated to 0 means, so at the maximum point the slope is 0. That's why, so the differentiation of power with respect to DL must be equal to 0. At DXL equal to 0. So again differentiation of U by V rule here. So V into, so R plus R by L, R plus RL whole square plus X plus XL whole square, so V into, so differentiation of U, that is where V square is constant, differentiation of RL with respect to XL, where RL is constant here, but we are differentiating RL with respect to DXL, that's why, so the term is 0, because RL is constant here, we are differentiating the power expression with respect to XL here, that's why the differentiation of constant is 0, so minus So v into, so u into v square into RL. So differentiation of v. See here r plus r by l whole square is also constant. So x plus xl whole square. So under x plus xl whole square, xl is a variable. So you can differentiate the second term here. So 2 into x plus xl. 2 into x plus xl. So must be equal to 0. Must be equal to 0. So the first term is 0. So r plus r whole square plus x plus xl whole square into v square into 0. So because RL is constant here, differentiation of constant is 0. So the first term is 0. First term is 0. Again the second term, so v square RL. So 2 times 2x plus 2xl. 2xl equal to 0. From this you can write down the expression as directly. So XL, the load reactance equal to XL is equal to minus X. XL is equal to minus X. So here V square won't be 0 here. We can equate X plus XL. Can equate X plus XL equal to 0. From this XL is equal to minus X. So this is the maximum power transfer condition. So at this value, when XL is varying, when XL is equal to minus X, by that time the power is transferred from source to the load. So this is the condition for the case 4. Case 4. Coming to the last case, so the mixing of 2. So now again the type of network is AC and the impedance, input impedance is R plus jX, and the complex load having again 2 parts here, resistive part, inductive part, both are variable here. So third case only RL is variable, fourth case XL is variable. Now both the variables, load variables, both are variable. Now again the same process here, same process. So first write down the KVL equation. From KVL equation you can write IL. So IL or modulus of IL, directly I am writing modulus of IL bar, that is V by, so square root of R plus RL whole square plus X plus XL whole square. This is the modulus of I, and the power expression is again the load power is always the power is consumed by the resistive part. So you can write PL equal to, so modulus of IL whole square into RL here. Now here we are having two elements or variables here. First I have to differentiate the given power expression with respect to XL, and then I would have differentiate the power expression with respect to RL. So 2 times I have to do the derivation differentiation here for getting the maximum power transfer condition. Already in the case 4, already I have seen that. So differentiation of power with respect to XL. Already I have seen that. By the time we got the expression as XL is equal to minus X. So when differentiation of power with respect to XL, so we'll get the condition is maximum power transfer condition is XL is equal to minus XL. XL is equal to minus X. So again with the help of this condition we can do the second one, that is differentiation of power expression with respect to the RL, that must be equal to 0. Now put XL equal to minus X. Put XL equal to minus X here in this expression. Again the power expression, or you can write current expression. So IL bar equal to so V by square root of, so R plus RL whole square plus, instead of XL here, instead of XL you can put minus X here, X plus XL, instead of XL you can put minus X. So instead of XL you can put minus X whole square. So the second term is 0. So modulus of IL bar equal to, so V by square root of R plus RL whole square. R plus RL whole square, second term is 0. So this is the modulus of IL. Modulus of IL again. So write down the expression for power here. Write down the expression for power here. For the second case, so power equal to, so V square. So I square by, so V square by I square into R, that is I square is V square by R plus RL whole square. R plus RL whole square. Now differentiate the power expression. Differentiate power expression with respect to the RL now. With respect to the RL, that must be equal to 0. Right? Again apply, so do a differentiation of U by V rule here. U by V rule. So that is V into R plus RL whole square into RL here. So V square into differentiation of RL is 1 minus, so U into, so V square into RL, so differentiation of V, that is differentiation of x square is 2x, that is you can write 2 into r plus rl, r plus rl, r plus rl, that is equal to 0, that is equal to 0. So by solving this equation, we'll get the load resistance equal to source resistance. Source resistance, that is when differentiation of power with respect to RL. Now combination of two. So when you're taking inductive reactance as a variable, by that time the condition is XL is equal to minus X. So when you're taking load resistance as variable, by that time the load condition is RL is equal to R. Now if you're writing the combined here, you can write, so the load impedance, so R plus JXL, you can write, so R minus JX. Instead of XL, you can write minus X. So this is the condition. This is the condition. From the condition, you can write, so Z. So Z source or Z load. ZL is equal to, so Z Thevenin conjugate. Z Thevenin conjugate or complex conjugate. So here already I have written the statement here. So when you are having load resistance and inductive reactance, both are variable. So the maximum power condition is, so the maximum power is transferred from source to the load when the load impedance equal to complex conjugate of source impedance. So this is the condition. So this condition is very, very important for this case.